Hello, this is the final project presentation for the Advanced Energy Systems course. This presentation is presented by me, Omar Assam Khunnais, and my group colleagues Muhammad Ali and Janital. In this presentation, we'll talk about an overview of different types of bidirectional DC to DC converters, starting with introduction and background of these type of converters, then moving to review different schemes, and then provide some simulation result for this converter. Now let's start with the introduction. Recently, the use of renewable energy resources has been increased to save the environment and remaining fossil fuels, and the requirement of storing the energy is also increased. In many applications like electric vehicles, the need of interfacing of energy storage with load and source is increased for a reliable and efficient system. Bidirectional DC to DC converter is the main device used to interface the battery and supercapacitor as a storage device to increase the system reliability. Moreover, in electric vehicle, bidirectional DC to DC converters used for capturing the kinetic energy of motor and charging the battery during regenerative braking by reverse flow of energy. Similarly, the output of the hybrid system in the consisting of wind energy, solar energy, and all other renewable sources are environment dependent, so fluctuation of power, output power, and sudden change in load demand makes these hybrid systems unreliable. So, the solution for this issue is to use of a storage system like battery supercapacitor with the help of bidirectional DC to DC converter for power conditioning and smooth flow of power to the load. In industrial application also, bidirectional DC to DC converters are used in many applications because devices are switched on and off at high frequency. So, dual active bridge isolated bidirectional DC to DC converter provide with both galvanic isolation, storage of surplus energy, and efficient flow of power without wasting the energy. For a proper understanding of hybrid energy system and electric vehicle, it's necessary to have knowledge of the working principle of DC to DC converters. Now, regarding the bidirectional DC to DC converters, the traditional buck-boost converter operates only in one direction. Unlike those, bidirectional DC to DC converters allows the power to flow in both directions. It could also be used to step down or up the voltage. Bidirectional DC to DC converters acts as power flow controller in both directions. Wind energy and solar energy as power sources output power is unstable and keep changing based on the environmental conditions. These systems are undependable and cannot be fed to the system with power due to considerable variation in their output. Therefore, these systems are always connected to storage systems such as batteries and supercapacitors. These storage systems start storing the excess power when the load consumption is low, and then use this stored energy to back up the system during failure and fluctuations due to weather conditions. So in this case, the bidirectional DC to DC is required to permit the power to flow in both directions. A standard DC to DC converter could be converted to a bidirectional DC to DC converter by adding a diode anti-parallel with a MOSFET or IGBT switch to let the current flow in both directions. Now, there are two types of bidirectional DC to DC converters based on the isolation between input and output, and can be distributed as the following: non-isolated bidirectional converter and isolated bidirectional converters. And my colleagues will expand more in the following slides on both types and discuss further the operation for both types and the simulation for the basic isolated bidirectional DC to DC converter.
Now I'll be talking about the types of the non-isolated bidirectional converter. We have three types of non-isolated bidirectional converter. One is the bidirectional buck-boost converter, where a buck converter is connected in antiparallel with a boost converter with an extra characteristics that allows the power to flow in both directions. The second one is the cascaded bidirectional buck-boost converter, which can operate in 4 quadrants and works as a buck and boost in both directions, which make it the most feasible topology. But it has also disadvantages, such as having more switches will lead to more losses, and the control scheme for this circuit might be complicated. The last one is the bidirectional true converter, which has a lower ripple among all the topologies. Isolated bidirectional converter is widely used in many applications instead of non-isolated bidirectional converter because of its galvanic isolation. To secure the source from any damage caused by the overload, A high-frequency transformer is used in isolated bidirectional converter to provide galvanic isolation. It is also used to decrease the noise. There are many schemes for this type of converters. Among them, the highly used schemes are half bridge and the full bridge due to their high efficiency. The dual half-bridge isolated bidirectional DC to DC converter is easy to control and has the highest power density. It has an efficiency between 92 to 94% and is widely used in electric vehicle applications. On the other hand, the dual-active full-bridge isolated bidirectional DC to DC converter is highly efficient for hybrid systems. This type of converters has the highest power capacity of any other scheme and has about 95% efficiency. In this project, we used a non-isolated bidirectional buck-boost DC to DC converter as a part of a microgrid and run some simulations. Now, Mohammed will explain the simulation results we got for this project.
In this segment of the presentation, I will talk about the simulation results of this project. For simulation, MATLAB Simulink software was used. A microgrid concept was taken into consideration to demonstrate the non-isolated bidirectional buck-boost DC to DC converter operation. The figure in this slide is a Simulink diagram of a microgrid model. For simplicity, a 48-volt DC source represents a solar panel or any other DC source, for example, rectified AC power. The 12-volt battery indicates an electric vehicle for charging. A load is connected in parallel to the source and battery. The MOSFET switches, that is S1 and S2, are controlled by the pulse generator's gate signals, so that when S1 is triggered, S2 is kept off. The switching frequency of the pulse generator for controlling the switches is selected as 24 kHz. The values of the inductor and capacitors are chosen considering 10 to 20% ripple inductor current and 10% ripple output voltage, respectively. There are two modes of operation of this simulation. The first one is buck mode, or charging of the battery. In this operation, the DC source is powering the load and charging the electric vehicle or battery simultaneously. During the charging of the battery, switch S1 is triggered and switch S2 is turned off. On the right side of this slide, waveforms of battery charge status, voltage, and current is shown. It can be seen that the upward slope of SOC and negative value of current indicate charge status of the battery is increasing. During this mode, load voltage and current waveforms also show that the load was getting power from the source. In the second stage, that is boost mode or discharging of the battery, the source is assumed absent. The 12-volt battery voltage is boosted to 48 volt and fed to the load. Switch S2 is now turned on and S1 is kept off. Similar to the previous slide, the respective waveforms of both battery charge status, voltage, and current are shown on the right side of this slide. These waveforms illustrate that the downward slope of SOC and positive value of current indicate charge status of the battery is decreasing. This slide shows the load voltage and current waveforms during the discharging mode. In this project, different types of bidirectional DC to DC converters were studied, and simulation for non-isolated bidirectional buck-boost DC converter was performed. Based on the features of the converters, it can be said that for electric vehicle application, non-isolated converters are more preferred for their small size and lightweight due to lack of transformers. However, in the case of hybrid systems, An isolated converter is more suitable because of galvanic isolation. Thank you for viewing this presentation.